Hello everybody, yet again another video here on sequences and series. So we've seen now we can have an arithmetic sequence or a series, and now a geometric sequence or series. But one thing we've not talked about is, do geometric sequences always go towards an infinite value as a number of terms go to infinity, or is there another case where if the terms go towards infinity, the value of the terms actually converges to a particular value? So we're going to have a look and explore that idea in this session. But before we do so, there are 4 warm-up questions for you to have a go at to get yourself in the mood for some maths today. So here they are. Question 1 and 2 link. This is some year 12 trig, which can of course appear still in the A2 year 13 exams. Question 3, parallel and perpendicular lines. And question 4, a slightly trickier calculus question, but one which you should be able to solve with practice. So have a think about these on your own. Press play when you've done your best and you want to see the answers. So assuming you've done that, let's have a look now at the answers together. So question 1, solve for the interval for theta between -180 up to 180 for the equation 3 sine squared theta plus sine theta plus 8 equals 9 cos squared theta, giving your answers to 2 decimal places. So the trouble here is we've got a mixture of different terms. We're talking about sine squared and cos squared and sine, so 3 different trigonometric terms here. One thing we can do though, we can get it all in terms of sine by simply remembering the identity that sine squared plus cos squared is always equivalent to 1. So never ever forget this one. This is perhaps the most basic of all trig identities, one which you can't do without. So from that, you should see that cos squared theta is one and the same as 1 minus sine squared theta. And to make it easier to write, what I'm going to suggest is that we just allow the letter S to stand for sine theta. What we have now, 3 sine squared theta becomes 3s squared. Sine theta I can just write as s and plus 8. Now I can replace the cos squared with 1 minus sine squared. But of course, if I allow s to be sine theta, I can just write 1 minus s squared. So if we expand these brackets, we get 3s squared plus s plus 8 equals 9 minus 9s squared. So essentially this is just a hidden quadratic in terms of a trig function. If we get all the s squareds onto the same side, so if we add 9s squared to both sides, we get 12s squared plus s plus 8 is 9. Then if we subtract 9 from both sides to get it into a standard quadratic form, we see that 12s squared plus s minus 1 has to be equal to 0. Now at this point we can either factorise or just use the class whiz. I'll show you both ways. So if we wanted to do this by factorising, or factoring if you're American, this would factorise, if you try it, into 2 brackets. We get 3s plus 1, 4s minus 1 equals 0. Therefore s equals minus 1/3, or s equals 1/4. Or if we use the class whiz, that's absolutely fine as well, because the examiners will be fully aware that you may well have a fairly powerful calculator on your desks in these exams. So just to remind you how to solve quadratics using the class whiz, what we can do is go to menu, press option A, press 2 for polynomial, press 2 because it's degree 2. Any polynomial which is got highest power 2 is quadratic, so it's degree 2. So the coefficient of the squared term is 12. Then the x term we have just one s, so type in 1 for x. And then minus 1. And press equals and equals again. And you see, the same as what we had here, either it's a quarter, and the other solution is minus 1/3. So, of course, we weren't talking about s, we were talking about sine theta. So, in other words, sine theta is minus 1/3, or sine theta equals a quarter. I'm now going to divide these into two separate cases. So for this case here, we can solve for theta by doing sine minus 1 of minus 1/3. And this will give us what's called the principal value, in case you've forgotten. So first one, the principal value is that theta is sine minus 1 of minus 1/3, which would give us, well, let's see. So go back to the main menu. So shift sign, minus 1/3. Principal value for this one is minus 19.47. So let's think about this one first. So what we need here, or what I tend to teach, is the cast diagram. Some teachers use the graph, I use the cast diagram, each to their own. So here's a cast diagram. I know the principal angle is minus 19.47. Just check it's in range. Yes, it's in between minus 180 and 180. Minus 19.47 means that it's measured down here, like so. So the size of that angle is 19.47. Now, if sine is negative 1/3, we're looking for where sine is a negative value. S and A are where sine are positive, therefore C, which we just got, minus 19.47, and also T, these are where sine is negative. So we've got one valid root here, minus 19.47. The other valid root will be, if we go around to this T quadrant, if we go the positive way, we'll be going more than 180. We can't go more than 180. So to keep within the range of validity, we need to go around in the negative direction from here, like so. So this angle here will be 19.47. All these acute angles will be 19.47, which you hopefully will have remembered. So this red angle will be 180 minus 19.47. So our solutions for this particular value of theta are theta being minus 19.47, or this angle here, 180 minus 19.47, gives us 160.53, 160.53. However, because we've got round to T in the negative direction, we need to remember the actual size of the angle might be 160.53, but because of direction we write down minus 160.53 because we've gone in the clockwise direction. We now think about the second case of where sine theta is a quarter. So for this one, again we need to find the principal value. So we do sine minus 1 this time of a quarter, so theta is sine minus 1 of a quarter. Let's see what we get for this one. So shift sine minus 1 of 1/4. And this time we get 14.48 to 2 decimal places. We need a second cast diagram for this one, so here's one I made earlier. So there we have it. So what in fact I've done, I've wrote this 160.53 a bit too close to the cast diagram. There we go. So a quarter is a positive value. So we're looking at where sine theta is a positive value, which is in the A for where they're all positive. I've got that one already. 14.48 is that there. And so the magnitude of all these acute angles in between these diagonal lines and the axes will be 14.48. Now, to get to this S quadrant, where again sine theta will be positive, I'd need to go in the positive direction around there, which, as you can see, is the best part of a straight line. It's almost 180. It's going to be 180 minus 14.48. So that one here, 180 minus 14.48 gives us 165.52, and that'll be positive because we've gone in the positive anti-clockwise direction. So now we say that therefore from these two values, theta could be either 14.48 or 165.52. Now, to make it easy for the examiner, you want to make it as easy as possible for them to give you full marks. You write the full solution to conclude. So the full solution is listing all four values. So theta, the smallest it could be is minus 160.53. Or it could be minus 19.47. Going up slightly more, could be 14.48. Well, the final one, in blue, is 165.52. So quite long-winded, but that's all of question 1 done. Question 2 now links to this one, so let's have a look at the second question. So like I say, question 2 links directly to question 1, and you can see this if you look carefully at how the question is worded. So it does say using the result from question 1 or otherwise, and also look at the equation. The equation is almost exactly the same as the equation from question 1. So what we're going to do in a moment is compare them and see how they're the same and how they're different. We want the smallest possible solution of this equation, giving the answer to 2 decimal places. So we want the smallest x possible that will solve this trigonometric equation. So let's just remind ourselves what we had from part 1, from question 1. That's what we had from question 1, and we got that theta was these 4 values. Now, what we're being asked is this. So the coefficients are the same, that constant's the same, it's 9 cos squared and 9 cos squared there. So the only thing that's different, if you notice, is the theta from number 1 here has been swapped out and replaced with 2x minus 30. And so if we made 2x minus 30 to be the same as theta, it'd be the same equation. So if we're solving in terms of theta, and we had this, theta equals these 4 values, because it's exactly the same format, therefore 2x minus 30 would also be exact same values like so, because theta and 2x minus 30 are one and the same thing essentially. So which one of these 4 scenarios, which one of these possible candidates would give us a smallest value of x? Bear in mind, to make x a subject and solve for x, we need to add 30 and then half. So this one here, if we added 30, it'd still be negative. That wouldn't work. We want the smallest positive solution. However, this second one here, if we added 30 to that, it'd just go negative, so we could half it, and then it'd be even smaller. So this is the one we're wanting. That would be positive, but it would be bigger. That wouldn't be the smallest. That certainly wouldn't be the smallest. That would be the biggest solution. And so if we take this one here, add 30 to it, and then divide by 2, what we should get is minus 19.47, add 30 to it, like so, and divide by 2, yes, we get 5.27. To 3 significant figures, or 2 decimal places, which is what it's asking for. So that's the smallest x that satisfies that equation. Let's now have a look at warm-up question 3. So we've got line L1, which has the equation 4y minus 5x equals 8. So if I just take L1 and rearrange it, so we've got 4y equals 5x plus 8. And if I divide all by 4, y equals 5/4 of an x plus 8 divided by 4, which is 2. So therefore the gradient of the line L1 is 5/4. So L2, we're told it passes through minus 3 minus 4 and 7 minus 12. So I'm just going to sketch these points in. So minus 3 minus 4, I'll put this over here. And 7 is to the right, but I've gone down, because minus 12 is a smaller value than minus 4. So if I call that 7 and minus 12. So to work out the gradient, we need to remember it's the change in y divided by the change in x. So I can write this down. So the gradient of the line L2 is between these 2 points, change in y divided by the change in x. So we've gone from minus 4 down to minus 12. So we've gone down by 8. So you could have done as well, instead of that, minus 12 minus minus 4. Either way, the change in y is minus 8. And the change in x, we've gone from minus 3 up to 7. That's an increase of 10. So it's minus 8 over 10, which simplifies to minus 4/5. So if we compare these two now, L1 has this gradient, L2 has this gradient. And if you notice, one is the negative reciprocal of the other. That's telling us that these two lines must be parallel. A nice way to prove that is to prove that the product of the two gradients equals minus 1. So we can say, therefore, the gradient of L1 multiplied by the gradient of L2 is 5/4 multiplied by minus 4/5, which is minus 1. Therefore, L1 and L2 must be perpendicular. We can now finally think about the last warm-up question, warm-up question 4. Right, so we're told that a is a constant, and the integral of this expression from x being 9 from x being 1 equals a squared plus 13 over 3. We need to show that there's exactly 2 possible values as a and state these values. So if we're integrating this, what I'm going to suggest we do first of all is rewrite the radical in terms of a power. So if you're square rooting something, it's the same as doing that to the power of half. So we're going to integrate from 9 up to 1, and what that's going to give us is as follows. So we integrate, the power of the variable increases by 1, so we're going to have 4x to the 3 halves divided by 3 halves, with a minus a, we just tag an x on the end. X to the 0 becomes x to the 1. We're taking that between the limits of 9 and 1. Now it might help you, in terms of simplicity, to be thinking of this 4 divided by 3 halves. That looks a bit awkward, so I'd suggest you might want to just think of it as 8/3 x to the 3/2 minus ax. So if we substitute in 9 first of all, so what we'd have here, 8/3 multiplied by 9 to the power 3/2. That's going to give us 72. And then when x is 9, a times 9 gives us 9a, so we're going to minus off 9a. Then we're going to subtract off what we get when x is 1, which is much easier. 1 to the power anything is going to be 1, so that's going to give us 8/3 minus just a. So let's neaten this up. So 72 minus 8/3, well, we can do that. 72 minus 8/3 gives us 208/3. And minus 9a minus a, go away, Microsoft. Minus 9a minus a is minus 9a plus a, which is negative 8a. And so all of this integral here is actually just equal, in the end, to this. So this 208/3 minus 8a, that equals a squared plus 13/3. If we now add 8a to both sides, you can hopefully see how this is going to go now. We get 208/3 equals a squared plus 8a plus 13/3. Now if we take away 208/3 from both sides, so we get the quadratic equaling 0, we can attempt to factorise or solve. That's going to give us 0 on this side, equals a squared plus 8a. Now I wonder, what's 13/3 take away 208/3? Well, I had that 208/3 on my calculator here, so I can just take away that by pressing minus answer. So 13/3 minus 208/3 gives me minus 65. Now if you want to, you might be able to class with this, but because it's a show that question, it's probably worth investing the time showing a clear algebraic method. Now this will factorise. There are two values which will multiply together to give minus 65 and will add up to 8. And those two values are positive 13 and negative 5. So we've clearly shown there's two values of a at work, and therefore these two values of a are that a equals 13 or that a equals 5. Hopefully that's warmed you up. Certainly has me. Let's now have a look at the main bit of the lesson. We're going to have a look at geometric sequences again, the sum to infinity of a geometric series. Don't worry, it won't take an infinite amount of time. So, the sum to infinity of a geometric series. It's a valid question to ask. Now that we have a formula that calculates the sum of n terms of a geometric series, it's pretty natural to pose a question: will the sum of a geometric series approach infinity as n goes towards infinity? It sort of makes sense that it would, doesn't it? If you're adding an infinite number of things, surely the value would just keep going up and up and up and would get therefore infinitely big. Let's first of all look at two different cases here. So case 1 is divergence. So consider the sum of n terms of this series. So 2 plus 8 plus, 2 plus 4 plus 8 plus 16 and so on. So we need to remember what the sum of the first n terms is. The sum of n terms of a geometric series is a brackets Rn minus 1 over R minus 1. So here, the first term a is 2. The common ratio, these terms are doubling, so the common ratio is 2. So the sum of the first n terms is therefore a, which is 2 brackets 2 to the n minus 1 all over R minus 1, which is 2 minus 1, which is obviously just 1. So we've got 2 brackets 2n minus 1. So what will happen as n goes towards infinity? Well, as n goes towards infinity, clearly 2 to the power n will go towards infinity. So therefore, as n goes towards infinity, the sum of the series tends towards infinity. So that's going to become infinitely large. 2 to the power of a number, you're just doubling and doubling and doubling. So if you're going to double for near an infinite number of times, the number is going to become infinitely big. So that's when it diverges. It doesn't converge to a particular value. It diverges, grows, 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 up, unbounded, off to infinity. However, sometimes these will converge. And what I'm trying to get at here is how do we know if a sequence will diverge or if a geometric sequence will converge? For this one here, we've got the first term is 1, and the common ratio, half divided by 1 is a half, or a quarter divided by a half, again would be a half. So what's happening here is these terms are halving each time, so r is a half. So for this one, Sn is going to be the first term 1 multiplied by the common ratio to the power n, so half to the power n minus 1 all over r minus 1, which is a half minus 1. Well, a half minus 1 is minus a half, so the denominator is negative a half. If you're dividing by a negative a half, it's the same as multiplying by negative 2. So Sn equals minus 2, 1/2 to the n minus 1. And if we expand these brackets, minus 2, I'm going to multiply by minus 1 first. Minus 2 times minus 1 gives us positive 2. And then we're going to have minus 2 times a half to the power n. So now what's going to happen as n goes towards infinity? Well, as n goes towards infinity, what will happen to half to the power n? Well, if in doubt, you can try this on a calculator. Half squared means half times a half, which means half of a half. Half cubed means a half times a half times a half, which means half of a half, which should be 1/8. So as n gets successively bigger, we're halving, 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 and we just keep on halving, which obviously makes a value smaller. If we half a value, it decreases its magnitude by a factor of 2. So like half to the 10, half to the power 10 is pretty tiny. What about half to the 20? Very, very small. Half to the 30. Now in standard form it's so tiny. So if you keep going up and up, what you'll find here is this is going to be becoming more and more small, times 10 to the minus 30. If you really up the ante and put like half to 1,000, it's so close to 0, even the calculator's given up and said it's so close to 0, I'm going to call it 0. So as n goes towards infinity, half to the power n goes towards 0. And so Sn converges. In other words, the sum towards infinity converges to 2. It'd never quite get to 2, but it becomes infinitely close to 2, so you can never say it's any distance away from 2. The sum to infinity would be 2, technically, in the same way that 0.3 recurring is a third, in the same way that 0.9 recurring is 1. So, what made this one converge? What made this one diverge? Well, geometric means we're taking powers of things. The key thing here, the key difference, is this common ratio. Because we're multiplying, we're taking to the power of the common ratio, power n. So if the common ratio is greater than 1, a number which is bigger than 1 to the power n will keep growing and growing as n gets bigger and bigger. Whereas if the magnitude of r is less than 1, then it's a proper fraction essentially. So as n would increase, the power of a fraction would decrease and decrease as the power gets bigger. So essentially, if the magnitude of r is less than 1, the sequence will converge. And that is the take-home point of this. So if we have a geometric series where the common ratio has a magnitude of less than 1, the series will always converge to a particular value. Whereas if the magnitude of the common ratio of a geometric series is greater than 1, we'll have divergence. So we've got this result here. If the magnitude is less than 1, the sum to infinity will have a value, it will converge, and the sum to infinity is given by a over 1 minus r. So the best form of the equation to use is the one where we have 1 minus r to the n over 1 minus r. I'll show you how this comes to be. So we're just left with a and the r minus 1 part. It's because as n goes towards infinity, if the size of r is less than 1, r to the n becomes negligible. So r to the n tends towards 1. So this goes towards a times just that minus 1 over r minus 1. A times minus 1 is minus a, and then r minus 1 at the bottom. If we multiply both top and bottom by negative 1, you'll see we get a over 1 minus r. So if we're comparing a series rather, where we're thinking about its sum towards infinity, it's often best to use this version of the sum of a geometric series. It's often best to use, therefore, a, then writing the 1 first. 1 minus r to the n, all over 1 minus r. Because that link between the a and the 1 minus r is just clearer if we write it in this form. Let's have a look now at some worked examples together. So first of all, a fairly easy opener. Find the sum to infinity of this series. So half plus a quarter plus an eighth plus a 16th and so on and so on. From before, the sum to infinity is a over 1 minus r. The first term you can see as a half. The common ratio, a quarter divided by a half, or any term divided by the one immediately before it will give you a half. So we can just plug these values in. So if a is a half, r is a half, what we'll see here is that the sum to infinity will be a half over, well, 1 minus a half is just a half, and a half divided by a half is 1. how can this be? How can it not be going on forever? Well, I've got a little diagram here to try to illustrate what might be going on. So if you imagine this as squares, which are halving in size again and again and again, considering it next to a unit square. So this big square is 1 unit by 1 unit. So consider the lengths of each of these dark grey squares as we go on. So this is the first square here, second square, third, fourth, fifth, and so on until you can't even see because you need an electron microscope is getting that small. So half is the first one. That means there's half of the remaining length left. Half of a half is a quarter, so you've got half of that remaining length left. Then we fill in an extra half, but again, there's always a half left. So there's always going to be a tiny bit left, so we don't quite touch the top edge. From top to bottom would be 1, but we're never going to quite touch that top edge because there's always going to be half left over of the height before. So obviously these halves of each sizes are going to be becoming increasingly smaller, but there's always a microscopic distance left over. So it's never going to get to 2. It'll get very near to 2, it'll become infinitely close to 2. 2 is like an asymptote, essentially, linking it back to a year 12 idea. We'll get infinitely close to it, but it can never exceed it. So that's number 1. Sum to infinity of this one would go towards 1. Number 2. The sum of the first 4 terms of a geometric series is 15, and the sum to infinity is 16. Find the possible values of a common ratio r. So we need to remember both forms of the equations. Sum to infinity is a, if I put the 1 first, so 1 minus r to the n over 1 minus r, and also the sum to infinity. It's the same thing without this bracket, so it's just a over 1 minus r. Now we're told the first 4 terms, so we know what S4 is. S4 is 15. But again, we can write this in terms of this expression. So it's going to be a, brackets, 1 minus r to the 4, because the first 4 terms, divided by 1 minus r. Whereas the sum to infinity, we're told that's 16. But again, in terms of a and r, we can write this down as a over 1 minus r. So 16 is a over 1 minus r. Now, it's hidden within this expression here. If I think of this rewritten in this way, think of it as a over 1 minus r times by 1 minus r to the 4. So if I just partition this fraction away for a second, then what you can hopefully see, because 16 equals this, I can sub this in to there. So just honing in on this now, I can see that therefore this is 16 lots of 1 minus r to the 4. That equals 15. So a bit of a sneaky trick, but once you realise that sneaky trick, you can crack it, and now we can actually proceed, and it's relatively speaking not too bad from here on out. So if we divide by 16, we get 1 minus r to the 4 equals 15 over 16. Then what I want to do is to simplify this slightly if possible. So if I get the numbers onto one side and r onto the other, so I'm going to have 1/16 equals r to the 4. Therefore, what we can do now is just take the fourth root of both sides. So we can say therefore r is going to be the fourth root of 1/16. But like the square root, because the square root, the second root, is even, and power 4 is even too, this is when we need to consider both positive and negative answers. So r is plus or minus the fourth root of 1/16, which is a half. That's because a half times a half times a half times a half gives us 1/16. If you're not sure, just use the calculator. In fact, I'd always recommend using the calculator anyway. We can now do part B. So part B I'm going to do in a little box here. Just section it off. So I'll call this B, like so. So given that all the terms in the series are positive, find the first term A. So because all terms are positive, and you can write positive terms as just plus VE. Plus VE means positive values. This is standard parlance, this is standard maths teacher speak and standard examiner speak, so this will make sense to anyone marking a paper. Because all terms are positive values, this implies therefore that r has to be positive a half. Whoops, just made a smudge. R is positive a half. If the common ratio is negative, what happens is the terms oscillate between being positive terms and negative terms. So now we can use this to find the first term. We know what the sum to infinity is. The sum to infinity is 16. And that's a over 1 minus r. But now I know that r is a half, I can just sub in a half for r. So 16 equals a divided by whatever 1 minus a half is. Well, 1 minus a half is a half, or 0.5. So therefore a is 16 multiplied by 0.5, which just gives us 8. So the first term has to be 8. Question 3 is a previous exam paper question adapted slightly. So these are the sorts of questions you might encounter in the real thing. So in a geometric series, the common ratio is r and the sum to n terms is Sn. We're told that the sum of the first 4 terms is 8/9 of the way to being the sum to infinity. We have to show that r equals plus or minus 1 over root k, where k is some integer we need to find. So what we can do here is we can just write down what we know. So we can write down here S4 equals, it's going to equal a 1 minus r to the 4 over 1 minus r. And the sum to infinity is obviously going to be a over 1 minus r. So S4 is 8/9 of a to the 1 minus r. So what we can do here is say that this S4 thing, which is this, is going to be 8/9 of the sum to infinity, which is this thing here. So if we do this, we'll notice some things will cancel off. So a to the 1 minus r to the 4 over 1 minus r will equal a 8/9 of the sum to infinity. So it'll equal 8/9 of a times 1 minus r. Now, if you look here, there's quite a lot of cancellation we can do, which is obviously beneficial to us. So we've got an a at the top of both. That means if we divide through by a, we can do that. And because there's 1 minus r at the bottom of each fraction, we can multiply through by 1 minus r. Another way of thinking about it is we can just divide the whole thing through by a over 1 minus r. So because this is common to each, I can divide both sides by it, so it simplifies to 1 minus r to the 4 equals 8/9. And because we're only interested in what r is, we can do this because you're left with something that relates r to a value. So after cancelling off, we can say that therefore 1 minus r to the 4 equals 8/9. Then what we can do is we can get everything onto one side of the equation. And this is a show that question, so if we can refrain from button bashing, that's all the better, because you need to show clearly, because the question is saying show that. So if I get the 8/9 onto the other side, if I take 8/9 on both sides, I get 1/9 minus r to the 4 equals 0. Now you're thinking, well, why have I done that? Well, actually, here, if you notice, this is actually a difference of 2 squares. 1/9 is 1/3 times 1/3, and r to the 4 is r squared times r squared. If you weren't sure about that, what you could do is multiply both sides by 9. In fact, I'll do that just to make it clearer. So yeah, why not? So then I'd get 1 minus 9r to the 4 equals 0. Because obviously 0 times 9 is still 0. This is now a bit clearer, a bit more clear to see it's a difference of 2 squares. So I'll get 1 plus, well, the square root of 9 is 3. The square root of r to the 4 is r squared. So 1 plus 3r squared, 1 minus 3r squared equals 0. So therefore, either 3r squared equals minus 1, or this 3r squared equals 1. If we square something, and we're talking non-imaginary numbers, something squared is always positive. So we can't have 3 lots of a square number ever being negative, not if we're talking about real solutions. So this one isn't possible. So therefore, it's got to be that 3r squared is 1. Divide through by 3, we get r squared equals 1/3. Finally, square root, and consider both positive and negative roots. We see that r is therefore plus or minus the square root of 1/3. The square root of 1 is 1. The square root of 3 we leave as 3. And so that's how we arrive at this answer. Now let's have a look at an extension type question. The last one, then it's over to you to try some after this last worked example number 4. We've got here the first 3 terms of a geometric series are given below in terms of x. So I have x squared, x plus 12, and 2x minus 3. Firstly, we need to show that x satisfies the equation x cubed minus 2x squared minus 12x minus 72 equals 0. So it's geometric, which means a common ratio has to be the same between each term. So if that's the first term, that's the second term, and this is the third term, then one term divided by the one before it will always be the same value, because that tells us the common ratio. So in other words, the ratio of x plus 12 to x squared, which comes before it, must be equal to the ratio of 2x minus 3 to the x plus 12, which comes immediately before it. So we can set up this algebraic fractional relation. Now we can now cross multiply to solve this. So if we have one fraction equals another, then that one multiplied by that one will equal that one multiplied by that one. So now we can say, so x plus 12 squared must equal x squared multiplied by 2x minus 3. So if we expand out the x plus 12 all squared, we're going to have x squared. We take the product of these two and double it, so x times 12 is 12x, double that is 24x. 12 squared is 144. Then x squared times 2x gives us 2x cubed. X squared times minus 3 gives minus 3x squared. We need to get everything onto the other side of the equation, so I'm going to take away everything from the left, so it all goes onto the right hand side. So firstly, I'm going to subtract x squared from both sides. So subtract x squared from both sides. On the left, we'll end up with just the 24x and the 144. On the right, we'll have 2x cubed minus 3x squared minus another x squared gives us minus 4x squared in total. Next, I can subtract the 24x on both sides. And in fact, why not just subtract the 144 as well? So subtract that and that from both sides. So then we have 0 equals 2x cubed minus 4x squared minus 24x minus 144. We're almost where we need to be. But if you notice here, the 2x cubed needs to be x cubed, minus 4 needs to be minus 2. What we need to do finally is divide everything by 2. So if we divide both sides by 2, we can say, let's move along here, so therefore, halving everything, x cubed, half of minus 4 is minus 2x squared, half of minus 24x is minus 12x, and finally half 144 is 72. Therefore we have what we wished to show all along. So we've done part A. Next we need to show that x equals 6 is the only solution of that equation. So what I'm going to suggest we do is we let fx equal x cubed minus 2x squared minus 12x minus 72. Now we've been told here, quite kindly I might add, that x equals 6 is a solution. If x equals 6 is a solution, in other words a root, it should be that x minus 6 is a factor. So let's just try and see if f of 6, let's validate and check that f of 6 gives 0. So f of 6 will be 6 cubed minus 2 times 6 squared minus 12 times 6 minus 72. So check this on a calculator if you want to. In fact, I'd recommend that we do. So 6 cubed minus 2 times 6 squared minus 12 times 6 minus 72 does indeed give 0. Now this may well be, even in my opinion, overkill, because it says x equals 6 is the only solution, but I'm interpreting this as we have to show that x equals 6 is a solution. So we prove that f6 is a root. When x is 6, we have a root. So what we can say here, because that is a root, we can say therefore, using the factor theorem, x minus 6 is a factor of f of x. In other words, we can divide this cubic by x minus 6 and we should expect to have no remainder. So let's try that now. If you prefer the box method for dividing polynomials, I've got this over here in a moment, so bear with me, I will reveal the other method for doing these, but for now I'm going to do the long-winded polynomial long division, because I quite like it, as do some other people. It's not for everybody, so if you're not in this camp, I'll show you the other way in a moment. So let's try and divide x minus 6 into x cubed minus 2x squared minus 12x minus 72. So first of all, we divide x cubed by the highest power of x here. X cubed divided by x will give us x squared. Next we multiply this x squared by x minus 6. X squared times x gives x cubed. X squared times minus 6 gives minus 6 x squared. We now subtract. So minus 2x squared minus 6x squared. Minus and minus is the same as adding. So minus 2 plus 6 gives 4x squared. We now bring down the next term. So we bring down the minus 12x. We now repeat. So we now divide the 4x squared by x. 4x squared divided by x gives positive 4x. We now multiply 4x by x minus 6. 4x times x is 4x squared. 4x times minus 6 gives minus 24x. We now subtract. 4x squared and 4x squared cancels. Minus 12x minus 24x is minus 12x plus 24x, which gives 12x. And again, what we need to remember to do is to bring down the next term, which is the final term. Therefore, this next iteration will be our last, because there's nothing else to bring down after. So we go again one final time. 12x divided by x is just 12. Next, we take the 12 and multiply by x minus 6. So 12 times x is 12x. 12 times minus 6 is minus 72. And if we subtract, we get 0. So therefore, we can say that f of x, in other words, x cubed minus 2x squared minus 12x minus 72, we can say this equals what we're trying to divide by, x minus 6 multiplied by x squared plus 4x plus 12, which is what we got along the top. Doing it the box method, we would have got this. So this in the red divided by x minus 6 gives x squared plus 4x plus 12. So we've shown that x equals 6 is a root, is an answer, is a solution. Are there any solutions in this here? So let's consider x squared plus 4x plus 12. So does this have any solutions? Because we want to show that this can equal 0. So obviously x minus 6 can equal 0 when x is 6, which was given to us. So can we solve x squared plus 4x plus 12? Can we set that equal to 0? Well, if we go for trying to think about solving this one, then if it's solvable, if it has any solutions, we need to remember the discriminant. So the discriminant for this one is b squared, which is 4 squared, minus 4 times a, which is 1, times c, which is 12 here. So that's given us 16 minus 48, which is less than 0. So in fact I can just say that's going to be minus 32, which is less than 0. So now I can say, therefore, x squared plus 4x plus 12 equals 0 has no solutions, and so x equals 6 is therefore the only solution, which is what we wanted to show. Okay, we want to show that x equals 6 is the only solution. Finally, part C. Find the sum to infinity of this series. So for part C, we now know that x is 6. So if we sub x equals 6 into here, into the series, the first term, x squared, is going to be 6 times 6, which is 36. The second term, x plus 12, that's going to be 6 add 12, which is 18. And the final term, 2x minus 3, will be 2 times 6, take away 3, which will be 9. So the sequence we're going to have is this one, 36, 18, and 9. So we can see here, the first term's 36, and the common ratio, 18 divided by 36, if you want to work it out, it's going to be a half. The terms are halving each time. To calculate it directly, we can do that. I'll call this 0.5 this time actually, 0.5. So the sum to infinity, s subscript infinity, is a over 1 minus r. So that's going to be 36 divided by 0.5, which is 72. And then we're done, finally. So now it's over to you folks to try some on your own. So if you turn to page 75, exercise 3E in the Pure Maths book, try questions 1, A, D and G, then I'd suggest all of them from 2 through to questions 11. Thanks for listening. I hope you found that useful, at least to an extent. I appreciate it's a lot to take in. Some of these questions are quite tricky, but you know, this is A-level maths. It's not a picnic. It is quite difficult. You know the drill by now. If you're stuck, ask me in lessons, try and find me in class, send me an email, even put a comment in the comment section. However you can reach out, please do. So do consider subscribing, please hit like, and I hope to see you all soon. Until next time, take care.